Hi everybody. So we've been talking about the different kinds of things that we can get from light. We've talked about how the luminosity of the star is the amount of energy that it's putting out. But if we know the luminosity, once we can figure out the temperature, now we can use another tool that will allow us to determine the lifetime of the star, how it's going to live, how it's going to die, whether there's going to be a supernova, a black hole, all kinds of things from that. So that's what we're going to focus on now, is figuring out how to get the temperature from that. Let's get started. So we mentioned that light is information. So everything that we get from the stars is from light. So like we said, we've got to squeeze everything we can possibly get. What we're going to be working on here is finding the temperature. Now, here's the rainbow that you guys are most likely used to seeing. And this is what most people think of when they see, a rainbow in the sky or anything like this. But if I were to ask you, what is the brightest color in this rainbow? You would probably immediately say yellow. Well, maybe it is and maybe it isn't. Your eye have actually evolved under a yellow sun. The sun puts out most of its light in yellow, so your eye is most sensitive to that kind of yellow-green right about here, actually. So you're always going to see that as being the brightest color no matter what. So what we generally do, instead of trying to just estimate based on the color spectrum here, is we do kind of like a bar graph. So this is wavelength, which remember is also color. And then this is the intensity or the brightness in that particular color. And again, you think about it as a bar graph. So I've got just a little bit of ultraviolet here, but I've got a whole lot, as it turns out, of the yellow, because this happens to be the spectrum of the sun. But we can also see what looks like black lines here are actually dips, and we can see the different depths of those dips. Also, we can see that there's a second peak over here in the infrared. So we need to get used to being able to use this particular kind of spectrum, because this is going to give us more useful information a lot of times than the color spectrum from this. So to get this kind of spectrum, we take this hot, dense, glowing object, a star in this case, and we have it shine through a prism, one of those triangular little pieces of glass, and then that will break it into its component colors. And here again, probably the yellow looks like it's going to be brightest to you, but in this case, it's actually the blue that's brightest. And you can see that because it's putting out more in that blue than it is anywhere else. Now keep in mind, all the colors are there. It's just that we've got more of the blue than anything else. The fact that all the colors are here means it's white light. But even though it's white, it's got a bluish tint to it. So when we compare the temperature of these different objects, we find that they change what their peak color is depending upon the temperature. And you may have seen this when you're working with your stove, for example. If you just barely turn on the stove, it's going to be a dark, dark red down here. But as it gets hotter and hotter and hotter, it turns more and more orangey from that. Hopefully it doesn't go to yellow, because then it's way too hot. But your water faucets are basically labeled backwards. Hotter objects are bluer. So you see that here we've got an object that's at 7,500 Kelvin. We'll talk about Kelvin in a minute. And you see that it's putting out most of its light in the blue right here. Whereas this one down here that's at 4,500 is putting out most of its light in red. Now I want to caution you on something. We're talking about where it is here on the x-axis, where it peaks. It is entirely possible to have a 4,500 degree star that comes up like this and then comes down. This is just showing you how bright the star is overall. So this star is going to be much more luminous than this star, but it's also hotter. And so that's telling us something about what's going on there. So keep this in mind. This is the key. Hotter objects are bluer. So let me move my video down here so that you can see. So this is the constellation Orion. And you may have seen this in the southern sky. We did this actually when we were talking about motions and star maps and things like that. But here's Orion's belt. This is a star-forming region. This is the Orion Nebula. This is where new stars are being born. So we're going to be spending quite a bit of time with this later on in the class. But then I want you to notice the two corner stars here. This star right here, this color kind of orangey red one here, is called Betelgeuse. I kid you not. And this one right here is called Rigel, which if you're a Star Trek fan, you're familiar with that. So notice that they're about the same brightness. However, this one is noticeably redder than this one. Now, when I was in college and I took my first astronomy class, and the teacher said, oh, well, there are red stars and there are blue stars and there are yellow stars. And I said, what, are you crazy? All the stars are white. And he said, no, really, they're different. If you go outside and you look at these, they are white, but there is a tint to that color. And Orion is one of the best places to see that, because you've got this strong red supergiant here called Betelgeuse and this bright blue supergiant called Rigel. So you can compare, and if you go outside, you can actually see that difference with your naked eye. I can talk about this till I'm blue in the face. or just go outside. You'll look out in the sky and you'll go, oh my God, I get it. So trust me, first time we get a clear night, go out, find Orion. Remember, you know from your own work, it's going to be in the southern part of the sky. And then see if you can compare Betelgeuse to Rigel, and you'll be able to see what's going on. So given what we learned in the last slide, which is hotter, Betelgeuse or Rigel? Well, remember, hotter objects are bluer. So Rigel must be the brighter one. It must be the hotter one because it's bluer. So the coolest star then must be Betelgeuse right here because it's redder. All right, move the camera back up. So I mentioned I would tell you about Kelvin and the different temperature scales. So let's talk about that for just a minute. Fahrenheit is what we use here in the United States. All temperature scales are based on when water freezes and when it boils. Fahrenheit freezes at 32 degrees. Water boils at sea level, at least, at 212 degrees. Now, this is actually also changes because if you're higher up in altitude with less air pressure, water actually boils at a lower temperature. So this is why if you're up in Flagstaff, for example, up in the mountains, you actually have to cook your food longer because water is boiling at a lower temperature. And when we're cooking things, we're actually heating the moisture inside what it is that we're cooking from that. But 32 to 212, that is a bizarre temperature scale. That just really doesn't make any sense whatsoever. This came about in about the 1600s from there. So most of the countries in the world use the metric system, which is Celsius. You'll also hear this as centigrade. You'll see why in a second. And in the Celsius scale, water freezes at 0. Makes perfect sense. Water boils at 100. It's a nice even scale. If I'm at 50 degrees, I'm halfway between freezing and boiling. And the reason we call it a centigrade scale is because cent means 100. There's 100 degrees between freezing and boiling. So that works out really well, and this is what you'll find. Just to give you some references, your body temperature, which you know in Fahrenheit is probably 98.6, somewhere in there, that's going to be about 39 degrees Celsius. A hot summer day here in Phoenix might be about 42, 43 degrees. A nice cold glass of water might be 15 degrees Celsius. Room temperature, normal room temperature, would be maybe 25 degrees Celsius. So kind of keep those in mind. I'll never ask you to spit those back to me. I just want you to have kind of a feeling for what these temperatures are with that. Now, in science though, we are lazy. We don't want to have to use negative numbers. I mean, seriously, do you like negative numbers? Probably not. So right now, anything that's colder than 0 degrees Celsius is going to be a negative number. Well, we don't want negative numbers. So why don't we take that same scale and slide it all the way down to absolute 0? So that absolute 0 is the coldest possible temperature, and we'll make that our 0. Well, absolute 0 in Celsius is negative 273.2 degrees. So all we need to do is just add 273 degrees. So the formula looks, if I can find my pen, there we go. So the formula looks something like this. The degrees in Kelvin is equal to the degrees centigrade plus 273.2. So if I'm at absolute 0, which is negative 273.2 plus this, that puts me at 0 Kelvin. So water freezes then, let's do this together. Take the 0, you plug that in there. 0 plus 273.2 is 273.2. So water freezes at 273.2. Water boils, put in 100 here, and I get 373.2. But do you see that there's still 100 degrees between water freezing and water boiling? So Kelvin is exactly the Celsius scale. The only difference between it is that we don't have any negative numbers. And hey, that's great, right? So we're going to be using the Kelvin scale for pretty much everything that we do here in class. So anytime you're working with a temperature, just make sure you're in Kelvin, you'll be fine. We will almost never be using the Fahrenheit scale. There's just no reason for it in science. All right, so Wien's law is that relationship. We just discovered that hotter objects are bluer. So that's all that Wien's law right here says. Now you remember from last time that this little symbol, this lowercase Greek letter lambda, means wavelength. So call it chicken foot, I don't care. So this is the wavelength, and we mean the peak wavelength. And so if I were drawing that curve that we saw here, this is the wavelength. Only one number is going to be the maximum. I'm not interested in reading off what that value is. I want to know where it happens down here. So I just find that peak, come straight down, and I read off that value right there. That's the peak wavelength for that. Now, hotter objects are bluer, so think about it, are blue objects, if something's bluer, does it have a long wavelength or does it have a shorter wavelength? Think about it. Gamma rays are blue. Do they have a long wavelength or a short wavelength? So they're going to be very short. So let's suppose that I've got a shorter wavelength here. So as the wavelength goes down, these are inversely proportional. So the temperature goes up. So if the wavelength gets shorter, it's bluer, and the temperature goes up. Hotter objects are bluer. So this formula here doesn't say anything more than what we've been saying in words. Remember, don't get lost in the math. The math is not the science. I am much more interested in you learning the science than I am learning the math. Yeah, I want you to do the math, but it's important that you understand the concept behind it. So all this says, literally, all this says is hotter objects are bluer. So to actually calculate a number then, I would take 2.9 times 10 to the 6, and in Smart Sparrow it'll give you, a whole lot more significant digits than that. But take that, divide by that peak wavelength, which has to be in nanometers, by the way, and then you'll get the temperature in Kelvin. So remember, everything's going to be in nanometers, and I asked you in the last one to memorize the range for the visible. So the longest wavelength, the red, is going to be about 750 or so. The shortest wavelength, the blue, is going to be about 400 nanometers or so. Anything shorter than that is probably going to be ultraviolet or X-ray. Anything longer than that is going to be infrared, microwave, maybe even radio. Okay? So if I know the peak wavelength, I've got the temperature. So this is the tool that you're going to be using for this section. All right, so look on your class notes, and we've got this diagram here. What color does Rosa appear? This is Rosa right here. And we're showing you the peaks right here. That's what these dashes are showing you. You read it off right here. This is violet, blue, green, yellow, orange, and red. So the short wavelengths in this particular case we're drawing down here. The longer wavelengths we're drawing here. Get used to that. You've got to be able to see it in both directions. I should be able to have the long wavelengths on this side, or I can have the short wavelengths on this side. Don't get confused, but always read the scale down at the bottom so you know where we're at. So what color does Rosa appear? Does it appear reddish or does it appear bluish? Pause the video and go ahead and figure that out. All right, hopefully you actually paused it, but just scroll down here and you're going, well, Kilo, it's not on the red or the blue. It's actually, somewhere between blue and green. That's true. But remember, there's only two colors in astronomy, red and blue. So it's a lot closer to being bluish than it is to being reddish. So Rosa then, we would say, is a blue star. It's a bluish star. So the next one says, what color does Overton appear? Here's Overton right here. And you see that it peaks right about here. So pause the video. Is that reddish or is that bluish? Well, this one then is going to be it's going to be peaking in the red, so the star looks reddish. Keep in mind that Rosa, for example, still has some red light. In fact, it's got more red light than Overton does. Do you see that? Remember, this is just a bar graph. So Overton only has this much, whereas Rosa has this much. But Rosa has even more blue light than it has red light. And so it looks bluish because of that. Overton, even though it doesn't have a whole lot of red light, it has even less blue light, so it looks reddish. Okay? So now you know Rosa is blue and Overton is red. Which one is hotter, Rosa or Overton? Pause the video, find out. You back? Okay. So Wien's law says hotter objects are bluer. I'm going to quiz you on that over and over and over. Hotter objects are bluer. Since this Rosa is bluer, that one's hotter. All right, so now we want to test that you can actually do the calculations. There are times when I don't just want to know which one's hotter, which one's bluer, and so on. I want to actually get a temperature for that. And so that's what we want you to do now. I'm telling you that Rosa peaks at 414 nanometers, and that's fairly blue. And then Overton peaks at 725 nanometers, which is pretty red. That's pretty extreme red right there. So what I want you to do now is pause the video, and we're going to work out what these answers are for this, okay? So all you need to do is you take the formula that you see up at the top, the 2.9 times 10 to the 6th, divide by 414, and then that's going to give you the temperature. All right, I've called up our calculator here online. Hopefully you're using your own, but let's go ahead and set this up. So if you're using the online calculator, remember you have to press OK to make that work. and then we're going to put in 2.9, and then this would either be your x10x as it is here, or maybe EE or EXP or whatever. So x10x and then 6. And on this particular calculator, I don't like it, but that's the way it is. You have to hit the right button here to get it to come back down. So 2.9 times 10 to the x10x, 6. And now divide by the wavelength, which was 414, hit equals, and there's our answer, 7,000 degrees Kelvin. Notice that you would not want to put all these numbers in here. You only want 3 significant digits. Since this is less than 5, we round it down. And so this comes out to be 7,000 Kelvin. All right, so you do the next one. So in this case, the peak wavelength is 725. So remember, we're talking about where it peaks right here. You see where it's at the top, you just come down and you read off that value. And I'm telling you that it's 725 nanometers. So pause the video, work out the temperature. Okay, back with the calculator. So this is going to be exactly the same way, 2.9 EE, EXP, X10X, X10N, whatever your particular calculator is, 6, and then in this one case you have to hit the right button. You may not on yours, and that's fine. Divide by, and then we said it was 725, and I'm getting 4,000 Kelvin. So hopefully that's what you're getting as well, is 4,000 Kelvin. Notice that I didn't hit equals after I put in 2.9 x10x or EE6. It's just a number. It's not a formula, it's just a number. So just put that in and then just treat it like any other number. Okay, so now you've seen how to calculate the temperatures. You could go the reverse. If I gave you the wavelength or the temperature of an object, like your body temperature, then you should be able to figure out what peak wavelength you're actually radiating in. And you do it the same way. You just have to solve that Wien's law equation for lambda max instead of for T. And you'll have to do that in the lab, and it'll give you an example of how to do that when you get a chance. Okay, so flipping over to the back. So we've got some options here. We've got ROSA and we've got GNFR. So, and then you've got some characteristics and some analysis. The first one says, which one peaks at a longer wavelength, ROSA or GNFR? Pause the video, think about it, and then come back. Okay, so just a reminder, don't just wait for me to keep going. This is not Dora the Explorer. Ask a question, pause, give you the answer. No, you really do need to pause the video so you can work this out. All right, notice that both ROSA and GNFR peak at exactly the same wavelength. So they would actually be the same. Do you see that? They're right on top of each other. They're peaking at the same wavelength. All right, so given that then, which has the lower temperature? Pause the video and think about it. Well, if they peak at the same wavelength, they've got exactly the same temperature. Hotter objects are bluer, but neither one of these is bluer than the other. They're the same color, so they're the same temperature. Don't get fooled by how tall they are. How tall they are, how tall that peak is its luminosity. That is not its temperature. Temperature is always measured using the wavelength down here. Luminosity is what's measured here. So they have exactly the same wavelength. And if you think about it, if you figure out the peak wavelength here, if you put that into Wien's law, you're going to get the same temperature for ROSA that you do for GNFR because it's the same wavelength. So they have exactly the same surface temperature. Next one asks, which one appears reddish? You know the drill. Pause the video, work it out. All right, well, they both peak over here. Neither one of them is red, right? And which, of course, gives you the answer to the next one. They're both peaking in the blue here. Do you see that? So therefore, they must both appear to be bluish. Then the next one, the last one says, which has the greater energy output? Now we're actually talking about the luminosity. So GNFR comes to right here, whereas ROSA comes to right here. So which one has the higher energy output? That's right, ROSA has the higher energy output. Okay, so that's how we read this graph. And learning to read this graph is going to be very important for a lot of the work that we do later on. All right, so here's a second example down at the bottom of the page 2. And it says, here's ROSA and here's SORTHO. So ROSA peaks here, SORTHO peaks here. So which one peaks at a longer wavelength, ROSA or SORTHO? Pause the video, think about it, and write down your answer. All right, well, you might say, well, neither one of them peak in red. That's true. However, Sortho peaks closer to the red than Rosa does. There's only two colors, so we say that this is a red star. And then if you look at the longer wavelength, this has the longer wavelength, so it's reddish. That's this question here. Skipped one here, forgot the lower temperature. If Sortho is reddish and Rosa is bluish, which one is the lower temperature? Hotter objects are bluer, cooler objects are redder. Since Sortho is redder, it must have the lower temperature. And then we said this one appears reddish, and then you see Rosa, same, still peaks in the blue like we had before, so that one appears bluish. Now the last question, which one has a greater energy output? Don't get confused between energy output, which is luminosity, and temperature. Energy output is how much they're peaking up here. Well, both Sortho and Rosa peak at exactly the same height, so they have exactly the same energy. They're the same luminosity from that. Okay, so, and let's go back to our picture here. I'm going to move the camera back down. This is like Sortho, and this is like Rosa. Sortho is just as bright as Rosa. Now, realistically, this is Betelgeuse and Rigel, but comparing to your graph, they're the same brightness. They have the same energy output. Yet this one is redder than this one. So this means that Betelgeuse, in reality, must be much cooler than Rigel is because it's redder. And this also tells you, though, that they're the same energy output. So that's on a graph, that's going to look just like what we had before. So we'll move the camera back up here. It'll look like this. Same energy output, Rosa or Rigel is going to be bluer, Sortho or Betelgeuse is going to be redder. All right, so from the continuous spectrum, that's what this is called. It's called continuous because it's a rainbow, and this is a rainbow. Try to see this as a rainbow. I've got all of the colors are present, but I've only got a little bit of some of them and a whole lot of some others. But it is a rainbow, all of those are there. So this is a continuous spectrum, no dips, no nothing. That tells us the temperature. So that's the first thing that we're going to get. We're also going to end up getting the size from that, but that's for the next lecture. So the tool for this time then is Wien's law. Hotter objects are bluer, that's what it means in words. This is the tool in math. And remember that the temperature has to be in Kelvin and the peak wavelength has to be in lambda max. Now remember, just as a reminder, when you're in the lab, you're going to see this whole number spelled out with all of its significant digits, all the way down to like 0.5 or something like that. I want you to confirm for yourself that that number is actually 2.9 times 10 to the 6th, okay? All right, so I want you to download the Finding Temperature practice. Make sure it's gonna look like this. It's gonna give you 2 problems, nothing on the back. As always, scan it, upload it. Okay guys, that's it for this one. Now, in the next lesson, we're going to be talking about this, using the continuous spectrum to get the size. And just to give you kind of a preview of what's going on, if you think about our graphs here, we saw that, for example, Betelgeuse was just as bright. It had as much luminosity as Rigel did, yet it was much cooler. Think about that. How could that possibly be? Well, the only way that could possibly be is if Betelgeuse is much, much larger. So if I know the luminosity and I know the temperature, now I can get the size. So that's what we'll be talking about next time. I'll see you then.